Hi, welcome to Calculus 3. Today's lecture is about surface area. We have a surface in space. We want to find the area of a portion of it that's above a certain region. So, for example, here we have a surface is given by the equation z is equal to some function of x and y. Down here, we can have a region of any shape. Here's a rectangle, but it could have been anything. This is a region R. We want to find the surface above this region R. We are going to show that it is a double integral of this expression, which is square root of 1 plus partial of f with respect to x squared. So we take the function, take the partial of it, square it, and the same for partial with respect to y in square root times the element of area. The element of area is, of course, is in this region R. We want to go ahead and explain where does this formula come from, and then we are going to do an example. Uh, in your text, you're going to see a derivation which is based on cross products and areas of parallelograms. I'm going to use a different derivation that's going to be kind of geometrical and perhaps somewhat more intuitive. Let's go ahead and review several basic facts so that when we put all of these things together, we are going to have this formula. Once we have it understood and established, we are going to come back and actually do an example of calculating area of a familiar item. Okay, several things to take a look at. Let's start with basic idea from trigonometry. So suppose we have a right triangle, and this is the angle theta in it, and the adjacent side, let's call it S, the hypotenuse, let's call it L. You remember from trigonometry that cosine of theta was the adjacent over hypotenuse. And if we rearrange this thing, we can write the L as 1 over cosine of theta times S. How this thing is going to be useful to us? S is going to be in the region R, and L is going to be a certain line segment we are going to look at in the surface itself. So S is going to act like a shadow, and L is part of an object that is causing the shadow. The relationship between the two of them is very simple. L is 1 over cosine times S. We are going to see that this 1 over cosine expression here, this expression here is for us is going to turn out to be uh, just that. Let's go ahead and proceed. Uh, Next item we want to pay attention to is that if I have a normal to S, suppose this is a normal to S, and for us this is going to be in the Z direction, so I'm going to call it unit vector K. So K is normal to S, and then a normal to L. So suppose this is L, and this is going to be the normal to my surface. Actually, I'm going to call it N. It is obvious that this angle theta that we are looking at here is the same as this angle here. The angle between two surfaces is same as the angle between the normals to those surfaces. This is a principle we use sometimes, helps us to find out angle between objects. So let's write this thing. Angle between two surfaces is equal to the angle between the normals to those surfaces. Okay, you hopefully you can go justify this thing, justify that this green angle here and this green angle here are the same thing, and of course both of them are complements this angle in between. Now another fact that we remember from our trigonometry or beginning calculus is that the cosine of theta, I can write it as n dotted with k divided by the length of n itself. So you remember n, the nk, the dot product property from perhaps your physics or calculus 2 classes. This was the length of n times the length of k times the cosine of the angle between the two of them. K is a unit vector for us in the z direction, so the length of that is equal to 1, and therefore cosine of theta is going to be n dotted with k divided by the or the length of n. So that is basic fact. Next fact that we are going to use is going to be the following. If I have a shape of a certain area, so suppose this is any shape, but here I drew a circle. If I take this shape and stretch it by a factor of 2 in a certain direction, so whatever it was, perhaps going to be turned into some sort of a oval looking region. So if the diameter of this thing was same diameter d, after I stretched it, say, suppose the diameter doubled. Yeah, we are stretching in one direction. What is it going to do? The area, the area of the red one also going to be double of the area of the white one. So if we stretch a object in one direction by a certain factor, its area also stretches by the same factor. This is very easy to see because every strip that we have in one of them has been stretched in the other one by a certain fixed factor, and therefore the entire area also stretches by that factor. So let's say if the area, if we stretch by factor of 2, then the area also doubles. And same way for any factor. Next, we are going to put these things together. Suppose I have, let's draw, yeah, this is my XY plane. And suppose I have a simple surface above it. Let's draw that thing perhaps in red. Now, if I have a rectangle here in the red surface, in the red plane, and the shadow of it in the XY plane here, down here. So the white one is the shadow of the red one. Suppose the area of the white one is the element of area of A, and the shape on the inclined plane, let's suppose the area of is dt. And let's suppose the angle between these two plane is theta. Then what's the relationship between the area? So I want what's the connection between the area of the red one and the area of the white one? Of course, the two of them are related by this angle theta. So any length in the red one is stretched version of the white one. What's the stretch factor? Stretch factor is just this theta. So what we have is that the element of the area on the inclined plane is 1 over cosine of theta times the element of area on the xy plane. So this comes from same relationship as here, because the length in the red one has been stretched by a factor of 1 over cosine theta. Okay, so each of these length are stretched by that factor, and therefore the area is also stretched by the same factor, just the discussion that we had here. Okay, now we go back to a topic we had a while back, which is if I have a surface that is given, if a surface is given by an equation like f of x and y and z is equal to some constant. So if we have an equation x, y, z and all of them on one side, on the other side we have a constant 0 or something else, it's all the same. And then the normal to the surface, normal to the surface is given by the gradient of f, which is, what was it, fx and fy and of course fz. That's going to play the normal. So what we are here, what we are after is catching the normal to the surface, because I want to figure this one in, and I want to figure the normal to well, the white one, the normal we know is just the normal to xy plane is just a unit vector k. I need my n to find out what is the angle between n and k, and then once I have that, then I can apply this formula and then I'll be all done. Let's see. So the equation that we have is given to us probably in the shape of z is equal to f of x and y. So what I do is I bring everything to one side, so I write it z minus f of x and y equal to 0. So that's going to be my capital F. Capital F is like this. Therefore my gradient is here. I'm going to calculate the derivative of all of this with respect to x. So that's just going to be minus f of x. With respect to y, minus f of y, because of this minus that we have here. And with respect to z is just 1. So that's gradient of f. So in this case, what is going to be n dotted with k over the length of n. So this is my n. Of course, who's k? K is the vector in the z direction is 0, 0, 1, of course. N dot k is, of course, is just 1. Length of n is just length of this vector. Length of this vector is going to be given by a sum of, so I take each of the components, f of x squared, f of y squared, and 1, I square them and add them up. So that is my n dot k. So so what was n dot k over n? That's going to be, of course, cosine of theta. That's the relationship we had. Cosine of theta was n dot k over n. So then, of course, 1 over cosine of theta is going to be reciprocal of this radical. Is going to be f of x squared plus f of y squared plus 1. Next, we said dt, the element of area on the surface in the space, dt is 1 over, so let me show this thing. Yeah, dt is 1 over cosine times dA. And so we did all this work to figure out what is 1 over cosine. It's equal to that. So dt becomes f of x squared plus f of y squared plus 1 dA. Well, we are 99% done. We found, let's just remind ourselves again, who was dt? dt is, excuse me, dt was this red little area on our surface. dA is the shadow of it on the xy plane. The relationship between the two of them is what we derived. Now, how about the total surface? Total surface, we are gonna find surface over R is gonna be double integral of this expression, f of x squared plus f of y squared plus 1 dA, and we have to integrate over the region R. So the whole problem depends on finding a nice expression for the region R, and for the function f, we need to calculate its partials and calculate this. Notice how similar this formula is to the length of a curve we had back in calculus 2 and also calculus 3. Let's take a simple problem to play with. You might remember calculating surface areas for surface of revolution from calculus 1. So let's pick one of those problems and do it in this style, and of course you can go back and do it again in the style of that you did in calculus 1. So we are going to consider a paraboloid. So I have z equal to x squared plus y squared. This is of course a paraboloid. Paraboloid, you remember, is obtained from taking a parabola and rotating it around its axis. So if you take a parabola here and then rotate it around the axis of parabola, that's what you get. We are going to try to find the area of paraboloid under plane, say z is equal to some numbers. Let's find a nice, well, it doesn't matter, whatever number, z equal to 25. So what is that? Z equal to 25 is a cut plane here, so it is like for us z equal to 25. We are cutting the paraboloid, and what we are after is this area. What is this area? Well, we need to know what's the shadow of that on the xy plane. Down here, the shadow of this is of course x squared plus y squared is equal to 25. So because this here, the radius of that is, we find that since z is equal to 25, it turns into x squared plus y squared being equal to 25. So the entire surface that we are hunting here is built on top of this circle on the xy plane. So the area we want to calculate, the surface area we want to calculate is double integral of, f of x, z of x, of course the same as f of x, that is 2x, and f of y, of course, is going to be 2y. So I'll have here 2x squared plus 2y squared plus 1. Element of area, let's write it, if you wish, dx dy. That's my element of area dA. And the region R is given by x squared plus y squared less than or equal to 25. The interior of that circle is what we are after. Well, we see that this construction has a circular symmetry, and so it makes sense for us to go to polar coordinates, the item we just looked at in the last lecture. Hopefully our integration is going to be painless in polar coordinates, and indeed turns out to be that way. So in polar, what was our dA? Our dA was, of course, r d r d, sorry, d theta. That was r dA. What is the description of region? Of course, r is ranging from 0 to 5, and theta is going full circle to 2 pi. So the area we want to calculate is going to be double integral. For theta, it's easy, from 0 to 2 pi. For r, we are going from 0 to 5. The expression itself, this is of course 4 times x squared plus y squared, which is just 4r squared. So I have 4r squared plus 1, and the element of area is r dr d theta. Well, this double integral can be calculated by separating the r and theta from each other. They're already separated, so I can do from 0 to 2 pi of d theta, and then I can do 0 to 5 of radical 4r squared plus 1 r dr d theta. This is of course trivial. This just 2 pi. How about handling this? Well, let's take a substitution. U is equal to 4r squared plus 1. So du becomes what? 8r dr. Therefore, r dr is 1/8 of du. When r is equal to 0, u is equal to 1. When r is equal to 5, u is equal to what? 4r squared plus 1 becomes 4 times 25 plus 1 becomes 101, some number. So 4 times 25 plus 1. So our integral turns into integral from 1 to 101 of, in the middle we turned into square root of u. Instead of r dr, we have du over 8. So let's integrate that. Is 1/8 of antiderivative of square root of u is going to be u to power of 3/2, of course, times 2/3. Is that right? U to power of 3/2, I have to multiply by 2/3. And all of that has to be between 0 and, 1, and 101. What's going to be left out of all of this? So this is going to be 1/12 of, and this expression is going to be 101 to power of 3/2, and then minus 1. So area, we had a factor of 2 pi here. We have to multiply that with what we have here. So area is going to be 2 pi times 1/12 of this peculiar looking number. We do one minor simplification again. Pi 6 of this 101 to power of 3/2 minus 1. That becomes area of this particular region. So what is this? This is the area of a piece of paraboloid that's between from its tip on the xy plane all the way up to the cut plane that is at z equal to 25. Now please read some other examples in your textbook for doing examples with different geometrical arrangements. So what did we achieve today? We have the following. If we have a surface in space given by z equal to f of x and y, we want to find the area of a chunk of it that is above a certain region R. We have a double integral of this particular expression. That radical is essentially 1 over cosine of theta. That's the angle that the surface making at that particular location. That's a stretch factor that you have, and that causes that particular expression that you get. Okay, until next lecture, good luck and God bless.